Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to the subject of machine design 1. We are right now in the process of designing a screw jack and we are solving a numerical. In the last lecture we have seen how the design screw was safe and how the nut was safe in shear and combined stresses. In today's session we are going to look at another aspect of screw design, which is called the crushing or the crippling of the screw. Now guys, we know that the screw like this will be if fixed in one end. See, failure happens when something stucks or the operation fails. Let us say screw gets stuck somewhere on the upper end and still the operation continues. It will experience the compressive loading both from top and from bottom. In that case, it may buckle or it may cripple or it may crush depending upon the length. So we have to see whether it is going to cripple or whether it is going to crush, and accordingly we have to see whether it is going to be safe or not. So let us go for the third part, and there we'll say design for screw crippling slash crushing. Now there comes another aspect which we can refer to the PSG of screw, and it says that we know that length of the screw, the total length of the screw, will say LS, will be given by the height of the lift HL plus H by 2, which is the height of nut. It's a standard empirical relation again. We have been given this parameter as 270 and this was found at 216. So the value comes out to be sorry, so length of the screw is 378 millimeter in our case. Now referring to PSG 6.8, we have to make certain assumption. Like I said, if it gets stuck, the screw gets stuck somewhere, we'll say that this end is fixed and this end is either hinged or free, right? So in that case we have to design this particular thing, because there are, of course, there are different chances whether both ends will get stuck, one end will get stuck and one end free, or one end get fixed and somehow other end gets hinged, right? So let's go for a very common and sensible case where one end will be fixed and another end will be free. So we'll say fixed, free, end conditions. So I'm referring to the PSG 6.8, and it says that for that there are certain theories. Of course, if you remember from the subject of strength of materials, there are basically two theories, Euler's theory and Rankine's theory. So for the considering the height and the dimension of this, the Rankine's theory will be a major one or the dominating one, and therefore using Rankine's theory, we have the crushing load or the crippling load is given by sigma c times area or core area will say plus 1 plus alpha divided by n, or factor c also you can say, into L by K square. This is a standard formula, empirical relation. We have to see whether the load or the stress are within the range or not. For this, there are certain selections again from PhD 6.8 we are going to make. We'll say n is equal to 0.25. It's a standard selection for the case that we have. Second thing we can take is length. Of course we know, which is 378 millimeter. We already have found this out. There comes K, which is radius of gyration. For this standard case, it is assumed that it is equal to core diameter divided by 2. So it somewhere comes out to be 24.5 millimeter. I'm sorry, core diameter divided by 4. There comes another factor that's called area, core area, which was 7543 millimeter square. We already have figured out this dimension in the first step. And sigma compressive is 260 Newton per millimeter square for the material of screw. Now we know that the ductile materials always have compressive strength slightly greater than the tensile strength. So its compressive strength is somewhere taken as same as tensile in our case, but this is how we can take the compressive strength. And using this factors, if I substitute in this particular formula, I'll get value of crushing load equal to somewhere around 1.79 into 10 raised to 6 Newton. The crushing value that we already have, the value which is acting on this particular is already smaller than this, right? And hence we know that W is actually the value of W which was given to us was 250 kilonewton, right? Somehow the allowable value PC is much greater than W, and hence I can say that the screw is safe in buckling, or you can say it is safe in crippling. And that is how all the aspects of failure of this particular screw which is involved in screw jack are proved. So it is safe in shear, it is safe in combined loading of uh, crushing and shear, and it is safe in crushing or crippling separately also. So there we end with the design part of this screw. Let's move ahead for the calculation of some of the important other parameters which are associated with this particular setup. So like we said, we are going to look at some other important dimensions. Of course, we know those dimensions from the diagram directly, so we can go for them. So it's D1 as the dimension, which will be given by means of P. So I'm not solving this particular thing. I'm going to elaborate the expressions. Calculation part I'll leave to the students. So we know that P is equal to, in terms of pi by 4 into d1 square minus d outer of this particular screw square into sigma t. So sigma t is the allowable value, right? So we already have the allowable value, the maximum value you can say. So sigma max we had was 53, so we'll go for 53 as the allowable value. So this is what the allowable value here is. I'll write it as max only. So we know this value of P, which is 250 kilonewton, into pi by 4. D1 is the unknown. So the value of D naught we already have is 110 square into 53. So based on this, we are going to get value of D1 in millimeter. That's the first parameter. Second parameter comes D2 directly. Again, it can be written in terms of force, and it's D2 square minus D1 square. Only thing is, this time it is compressive strength we have to substitute. P value, D1 value, compressive value we already know. We can find out D2 in this. We can go for the thickness of nut collar. If you see properly, nut has a collar given, right? T is the thickness of nut collar, and that can be found out using this formula. P is equal to pi D1 T. That is the maximum, say we will say. We have this value pi D1. This we can find out T value very easily. Next thing is D3. D3 is somewhere around 1.7 times your D outer. We already know this value of D outer. We can find out D3. The last thing is D4, which is the diameter of the pin which connects or which fixes the nut with the main frame. So that is basically 1/4 of the D3 value. So once we know D3 value, we can find out D4 also. So they are the major dimensions that we need to consider. Of course, there are certain dimensions which are associated with the handle, which are associated with the frame also. Somehow they come in proper proportion. For example, the outer diameter of frame and inner diameter of frame will always share some relation with the actual dimension or diameter of the screw. So it's a matter of standard selection. So let's not go into the depth, because as far as the screw jack design is concerned, this is the major thing that we are supposed to look at. So we can say that, or we can mention that remaining dimensions, let us specify, say handle, or let us say cup, or let us say frame, can be fetched or can be selected from the standard combinations, right? And this is how the first numerical of a screw jack design completes. In the next numerical, we'll go through different set of conditions which we will take apart and do this particular designing procedure in more or less same manner with some other aspects. Thank you so much for watching this video. If you like this video, please subscribe to Ekeeda.